Okay, welcome to this second part of the tutorial on cost function networks. It will be a practical exercise using the toolbar 2 solver, and we will model and solve problems, various problems in combinatorial optimization. So I invite you to go to this web page. Where you can find a description of the toolbar 2 solver. You can download it from GitHub. There is a documentation, the user manual, and also the various input formats it can read, such as the CFN format that we will use. But there are also others, such as the probabilistic graphical model UAI format or the MaxSat WCNF format, or even the pseudo-Boolean optimization format OPV. So now let's go to the tutorials. I will present three combinatorial optimization problems. The first one is the weighted Latin square problem. The second one is the frequency assignment problem with polarization, which was the subject of the RODEF challenge in 2001. And the last one is the block modeling problem. During my tutorial, I will do some comments, and they are all in this script, so you can find the commands and the output of the command you have, also with some text to explain what is done. So the first thing is to install toolbar 2. You have three possibilities. Either you have a Debian Linux distribution, so you can install the package just doing this command, or you download the source from GitHub. So I will do this. So when you get the source, you will have to install a few libraries that toolbar is using, and then using the CMake to compile it. So I go to the main directory toolbar 2 and do the CMake command, adding MPI option and also XML to read the XCSP2 all format. Okay, so now I can compile, and here I will use 20 cores for that. And at the end, you should get a toolbar 2 executable and put it in your main toolbar 2 directory. I will do this. If you don't find all the associated libraries, you can still compile toolbar 2 with just the GMP dev library and without the CMake by going into the subdirectory source and doing the following commands. So at the end, you should get the executable as me, and if you type the name toolbar 2, then it gives you the list of options the solver has, and also the various formats it can read. Okay. So my first problem is the weighted Latin square problem. This is a problem on the chessboard n by n, where you want for every cell to choose a value between 0 and n minus 1. And each row and each column must be a permutation of the n values. We add an objective function so that for each cell there is a cost associated to any of the possible values. For instance, this is an example of a solution for a 4x4 square example. The large numbers correspond to the assignment, and the small numbers correspond to the unary cost, and the red cost is the one corresponding to the chosen value. So if you do the sum of all the red costs, you got 45, which correspond to the optimum for this problem. I will use the CFN format to model this problem. So here, for this example, the CFN format, yes, it's JSON text file format, and you have three main sections: the problem, the variables, and the functions, the cost functions. In the first section, this inferior to 64 means that it is a minimization problem, and I want to find a solution strictly less than 65. Then you give the 16 variable names with their domain size 4, and next the cost functions. So here it corresponds to the soft or different on the following scope. So the first line corresponding to the first line in your chessboard, and the parameters are the violation measure for this soft global cost function. Here it is variable based, and the default cost is 65. It means that this constraint is in fact a hard constraint. I cannot violate it. So the same for all the lines, all the columns. And then here are the unary cost functions. So for each cell variable, the associated table of cost corresponding to the different value assignments. So if I want to generate this model for any size, I will use a Python script. So here you can download the script. It is using the a Python object, which is a dictionary, and thanks to arrays we can build for the range for all the rows, for all the columns. We will build the dictionary corresponding to each constraint or cost function. And there is a simple function within the script to transform this object into a CFN file format. So let's see on the shell. So I copy this script and execute it with 4, so I get the following output. I can save it into a file and now solve it using the toolbar to solver. It reads the 16 variables with the 24 cost functions, and you see the initial lower and upper bounds. The upper bound corresponds to the one in the file, so the 65, and the lower bound has been produced by soft local consistencies. And for the soft or diff, it corresponds to a mean flow max, a mean cost max flow algorithm. So then a first solution is found, and indeed it is exactly the same cost as the lower bound, so we have a proof of optimality on the solver end. If we want to see the solution with the names of the variables and their assignments, or we can use the following script to have a pretty print of the solution. So I go here and use a simple awk script for that. Okay, so now how many solutions there are in the problem? I can use option -A, and I say there are 576 solutions. How many optimal solutions there are? So for that I give an initial upper bound of 36, so I want all the solutions less than 36, and indeed there is just one. I can also look for a sequence of diverse solutions. And if I copy this line, I ask to find at most 10 solutions with diversity constraint, a Hamming distance of 16 here. So it means I want completely different assignments. So of course there will be only 4 indeed. So the 4 are here. The first one corresponds to the optimal solution, and then this is the best one with respect to the distance, so of 16 between the two solutions, and so on until I have found the 4th solution. Okay, so let's have a look to a larger instance. So I will use 8 by 8 Latin square. So now you can see solutions occurring during time, as time passes, better and better, and also an information about the optimality gap, that is a global lower bound and the current best solution. And this is thanks to a hybrid best first search algorithm that is used by default in toolbar. And at the end, you see it has reached the optimality proof. The best solution is 155 here. Okay, so this problem is quite difficult when the size increases. And I have made a comparison 10 years ago about the problem with other CP solvers like Choco and 6-tux Prolog. And instead of the all different constraint, I replaced it by the GCC global kernelity constraint. And for the 6-tux Prolog, it uses the GCC with unary cost, GCC with cost by region. As you see, when you increase the size of the problem, it goes rapidly high CPU time, and this is a logarithmic scale. But for this experiment, toolbar 2 with the EDAC GCC got the best result. Okay, thank you. Okay, my next problem is the frequency assignment problem with polarization. I have a list of radio links I want to establish between sites. Each link or path, you must choose a frequency, which is an integer value, and also the polarization that can be -1 or 1. You have a set of constraints. For instance, between two paths, I want the frequency must be equal or different. And also, I may have that the absolute difference between two frequencies must be greater than a given number, which is slightly less if the polarizations are different. So two numbers depending on if the polarization is equal or different. Those numbers depend on a given relaxation level L. And with smaller level of relaxation, those numbers are increasing, which means the constraint is more and more constrained. The objective function is a hierarchical objective function with 3 criteria. The first one, you want to find the minimum relaxation level K, such that at this level or higher level, all the constraints are satisfied. Then the second criterion is at the level K-1, you want to minimize the number of violated constraints of type 4. And there is a third criteria that for the rest of the lower levels, you want that the sum of the violations is the minimum. In order to model the problem, I will have only one variable per path, and it will represent both the frequency and the polarization. By doing so, I will be able to express binary cost functions and benefit from fast incremental soft local consistencies. So you can find the various input file from the RoDev challenge here or here. You will have also a description of the problem. Let's see a very small instance. Here, for instance, you have all the possible frequencies, 100 here for the domain 0. All the variables, only 4 variables, so 4 radio links. And here are the numbers. So for instance, for path 1 and 2, I want that the absolute difference of the frequencies at relaxation level 0, if the polarizations are equal, is 60. And here you see for the other levels up to 10. And if the polarization is different, it is slightly smaller numbers. Okay. So to generate the model, you will have to download this Python script here. Here it is, the main part about the model. So this is for the hard constraints. So you see it's binary constraints, and you have a table to represent the cost, which are either 0 if the constraint is satisfied, or top if it is violated. For the constraint of type 4, here it is when the polarization is equal. So if it is not equal, the cost will be always 0. Otherwise, if it is equal, if the absolute difference of the frequencies is greater than the deviation, it's okay, it's a 0 cost. Otherwise, it depends on the fixed level of relaxation that we choose. So we will not minimize the relaxation level, but we choose a given relaxation level between 0 and 10. So if it is higher than this relaxation level or equal to this fixed level, it means it is forbidden, so there is a top here. Otherwise, you have this second, the third criterion is if it is strictly at lower levels than k-1, it is only a cost of 1. Otherwise, it is a high cost at k-1 exactly. Okay, and the same for equality, when the polarizations are different between the two paths. Okay, so now let's see an example. So I copy the script and follow again my tutorial script, and indeed I would recommend to download this C program. It is the RoDev checker for your solution, and this awk script to do the job also. So compile the C code with this command and then execute this command. Okay. So I'm running the Python script to generate the model and then solve it using toolbar and check the resulting solution, which has satisfied all the constraints at level 3 or higher levels. This is what I ask here. And you see that at level 2, only one violation, and at lower levels the sum is 3 violations. Okay, so you can try to test a slightly bigger problem with 9 variables here. Example 2 with this command, and check again the solution, and the optimality proof has been obtained here. If we want to try larger instances that were used for the challenge, we need to take time to generate the CFN file corresponding model before solving them. So I have done this before the tutorial, and you can find all the instances by going to this link. So if I go there, you will get a repository of many benchmarks, cost function library benchmark, including the FAP benchmark, and you have the instances in WCSP format for some of the problems. So I come back to my tutorial. So download this instance and try with the default search of toolbar 2. So here I'm giving a 10-second time limit, and this instance, it has 150 variables with larger domains, so up to 300. And you see the solution found at 299 here, but it stops after 10 seconds. So instead of using a systematic search, I will use partial search with a large neighborhood search method. So indeed it is called VNS, so variable neighborhood search, and it's using problem decomposition. Here I'm using the min fill heuristic, and also I will add the -a to, which says that I don't want too many overlapping clusters. So again, the time to read the instance, it is quite large, and try to solve it using this meta heuristic, which uses a small neighborhood at the beginning, and it increases the neighborhood, here the number of discrepancies, when no solution has been found at previous level, up to 10 seconds. Okay, so I can do better. You see already it has improved a bit. It's 8.9 here, by using the parallel version of the VNS algorithm. So here. So now I run using MPI on 21 cores. There will be one master and 20 slaves. It means that the 20 slave will start from this first solution found by backtracking search algorithm sequentially, and then in parallel, exploring various neighborhoods, it will find the solutions up to this one, and it stops after 10 seconds, the time limit. but I have given this option to save the best solution found here. So now I can check if this solution found is the optimal solution or not. And for that I will use the default toolbar to search algorithm. So HBFS, giving it the input solution found previously here. So you see the input solution cost correspond to what has been found previously. And also this input solution, so it will be used as an initial upper bound, and it will be used also as a value ordering heuristic, and also as a variable ordering heuristic. And this is thanks to our new VAC integrality ordering heuristic that will be presented in 2 weeks at CP2020. Okay, so it tries to solve the problem, and you see the optimality gap, which is quite small. The total number of values in the problem, the number of non-unary cost functions, and you got the optimum. Okay, here it took 1 minute to solve the problem. Depending on the solution, it can be faster. Like here, it was 38 seconds. But anyway, we were able to prove the optimality for this large instance. And check the solution is correct with the checker. And if we look at the RODEF challenge, we can see that for this instance, toolbar 2, we have found a better solution, and that the best one found by the competitors at that time. I tried for a few other instances, and toolbar 2 got always a better solution, except for the largest instance with 350 variables, where here I need more time for VNS to find the same quality solution. You can see that for this solution it was not so hard, because VNS was able to end and so to get also an optimality proof in less than 30 seconds. Indeed, it was a better solution than the one known by the competitors. Okay, my third problem is the block modeling problem. This is a clustering problem which occurs mainly in social network analysis. It was the subject of the best paper last year at CP. So the problem is, given an input graph, you want to find a partition of the nodes into k clusters such that the interaction between the nodes in the input graph can be summarized at the level of the clusters. So it means that for the input adjacency matrix graph G, if you order the nodes with the partition, you have blocks of 0 or of 1 here, and this can be factorized by a m k by k matrix, such that when there is a 1 in this matrix M, it means the block should contain only 1, and vice versa for 0. This is a minimization problem, and we want to minimize the number of wrong edges. That is, when there is a missing edge in a block that should contain only 1, or an extra edge when the block should be 0. So this can be modeled again using a Python script. Here is the model. For that we are using ternary, so we are using m variables k by k for the factorization matrix, and the n variables for the nodes with domain size k. The objective function is represented by ternary cost functions. So for each cell of the M matrix and for every pair of two nodes, we have a ternary cost function which says that for this M cell in the matrix and for these two nodes, if they correspond to the same block and if the input edge is different than the one required by the M, then we have to pay a cost of 1, else it is 0. We also deal with safe loops, and we have added some constraint to partially break value symmetries on the node variables. So let's see on my simple example. So I copy the block model script and then I follow my tutorial script, so doing this command. For that you need to download simple math and also the awk script to pretty print the solution. Okay, so here again is the solution. So for 3 clusters with the factorization matrix and the partition of the nodes. So let's try on a more difficult example. So you will download here the political actor matrix. And here again the search occurs, and here it finds a solution of 26 and then prove its optimality. So this is for a 5 cluster problem. So it took a few seconds, 10 seconds more, and we have done a second model that you can find here. So block model 2, where we sort the nodes of the graph by decreasing out degree, and we also detect if the input matrix is symmetric. So indeed, if it is an undirected graph, to not generate all the M variables, because it will be also symmetric. So by doing so, so I just have, now I change to the block model 2 and solve the same problem again. So you see different solution that has been found, and again the proof of optimality, but twice faster. Okay, so we compare our results with the ones in the MathNet paper, and for the small data sets, the 4 ones with the largest number of clusters here, 4, 5, 5 and 3, here are the results in seconds, and we got better results for 3 of the instances, not on political actor, but still it's much better than the default CP model or even the MIP model. On larger networks, it makes a huge number of ternary cost functions. So this is about the maximum size that our approach can perform, whereas the CP approach worked with larger networks. Still, we have another local search method in Toolbar 2 that does quite well on these instances, and here you can see if I add the option -I, so using in-scope local search in pre-processing, I found the best solution directly, and then just have to prove the optimality. It was not faster here. Okay, thanks. My last example is about learning cost function network from solution data. We want to learn the user preferences based on historical solutions, and in order to make recommendation within a car configuration system. The idea is that the user selects some variables to configure the car, and the system make a recommendation for the most preferred value based on previous user choices and also on the learned user preferences. So let's have a look to the Renault example, and have a look to the README. And here come the original datasets we used. So it's a project with a French car manufacturing company, Renault, thanks to Hélène Fargier. We are interested in the following product description. Medium correspond to a small urban car, and big to a utility van with more product variability. And those product descriptions are a constraint satisfaction model where each variable corresponds to a different type of option, for instance which engine, the color, and so on. And the constraints are the compatibilities between the options. Some of the variables are implied by the others, so only a subset of the variables are decision variables that the user must select and choose a value. So our goal is to try to predict what will be the chosen value given the knowledge of the previous user choices and the learned cost function network. So for that we use historical data here. This is 1 year sales history. So each cell corresponds to a car configuration made by a user. So using this information we want to make a prediction for the most preferred value for the next selected variable by the user within the car configuration system, and we want that it corresponds to some possible feasible configuration with respect to the manufacturing constraints. So we will combine our learned cost function network with the product description, the CSP, the corresponding CSP. Now for that you need to go back to this link, and the CFN learn submodule you have to go there in toolbar 2 GitHub and perform the following commands to download the source and to compile toolbar 2 module for Python, so that you can have access to the toolbar 2 library from Python. So let's go again to the README for Renault. So the main script is renault.py, and before running it I will have a look to the complexity of the medium product. Okay, so here it is the number of solutions for the medium product, and I'm using toolbar 2 for that, with looking for all the solutions and using backtrack with tree decomposition. here you see the tree width, which is quite small compared to the number of variables, 148. Here the total number of feasible car configurations is relatively small, about 200,000. So now we can apply our Reno script to learn the cost function network corresponding to user preferences. And do an evaluation of the prediction of our recommendation system by doing a simulation of a user car configuration session. So first, using all the sales history, we use part of it for the learning part, so to learn the cost function network. And for that we are using convex optimization, which is quite fast here, and the resulting CFN has something around 300 binary cost functions. Then we will compute the precision quality of our prediction using other test samples, so the rest of the sales history. And here it is, so we go to the end. And you see there the precision at the beginning, so when the user has not choose any of the options, so it is already quite high precision, 81%, and then the user makes a choice, and then the system will recommend for the next selected variable what is the most preferred value, and you see the precision increases as the number of user choices are made. The problem to get the most preferred value corresponds to solving the cost function network with the partial assignment by the user choice and the mandatory constraints. This problem is never too difficult. As you can see, there is less than 200 backtracks. We have followed the tenfold cross-validation protocol to build to compute these curves. So the green curve corresponds to combining the learned model with the mandatory constraints, and this is compared to a naive Bayesian approach, which is the red curve, and to an oracle, the blue curve, which knows the test samples, which of course we don't for the other approaches. And you see that here this is just using the mandatory constraints, and here just using the learned preferences, and really it's much worse than using both together to get the green curve. So if you want to know more about this learning approach and the theory behind, I invite you to see the talk by Schiex on Friday. Thank you.